Hi everyone, in this video we will introduce you our recent work, trajectory and sway prediction towards fall prevention.
Falling is not only common in older adults, but also dangerous. Each year, 8 million people in the United States fall, and 1/3 of them result in very serious injuries. That's almost 3 million people hospitalized. For those over 65 years old, 30% of them experience falls every single year. So what if we can reduce that risk? Even by 10%, there will be 3,000 lives and $1 billion of medical costs saved. Think about 90%. According to a survey published in 2016, that would bring huge improvement to elderly's long-term health conditions, independence, and quality of life.
And that's why we created this project. Our physical system consists of 2 real-sense cameras that provides both visual odometry input and depth point clustering. There are also 4 additional IMUs mounted on different part of the lag to collect gait characteristics. So if we formulate the problem, we need to capture both the surrounding environment and the state of the user. Specifically, the environment is represented as a depth panorama, and the state consists of torso pose, velocity, sway covariance metric, gait frequency, and the joint angles. And then we predict the future states and latency in representation conditioning on the past states and the scene. The information would then be compiled in the format of depth panoramas, corresponding to the current viewpoint of the person. The VAE model would then encode the panorama and concatenate with the states, and the downstream LSTM will predict the future states in an autoregressive manner. Our system is also capable of predicting the expected panorama to see. For the loss function, we use info VAE loss to prevent mob collapse, L1 loss to improve the sharpness of the prediction, and a weighted panorama loss against depth to improve the reconstruction close to the current position. As for the data collection, the first stage is done when participants walking on a treadmill. Their body motion is tracked through mocap, and perturbations are issued to the waist in different direction and magnitude. And then the second stage of data collection consists of walking on campus in different scenes, covering outdoor, some light off-roading, and indoor, with diverse amount of environment features to interact with. The sway covariance ellipse is a key component in detecting external perturbations. It's calculated by projecting z-axis onto the xy plane and then fit a Gaussian distribution to the points. When the area changes quickly, that is a flag for potential external perturbations. Now, let's take a walk. In our viz, the orange lines are the predictions, and the green ones is the ground truth. The sway covariance ellipse are shown above the person. It's probably easier to see from the top-down view. You see, our vision model is able to pick up walls and top obstacles from the depth panorama and predict accordingly. But sometimes it still struggles when there are glasses in the scene, thinking it's penetrable. For example, the glass doors on the left. Thank you for tuning into our video. If you would like to know a bit more, please go to our papers.